Hello everyone, in this video we'll have a look at the simple BusyBox based Linux distribution anatomy. I'm going to the desktop and monkey see, monkey do Linux, which is the Git repository you can download from internet, from my GitHub basically. And here I want to say QEMU system and x86-64, so this is the 64-bit system. I want to say no graphic since I'm running this in the terminal. No graphic, and I want to use cursors for rendering. And the CZ-ROM image is monkey see, monkey do ISO, and also want to enable KVM for a faster virtualization. Finally, give this 1 gig of random access memory. So let's go for it. So this system should boot on both the legacy BIOS and the UEFI boots. Right, so I've replaced the monkey see, monkey do logo to the booting process, so that when we encounter a shell, it no longer display, because this might be annoying to some people. So let's start by running the whoami command, and it tells me monkey see, monkey do. So there was a Linux user called monkey see, monkey do created on this system. So I'm currently in the home folder. So if I do go to the root and list it there, so we can go to home, and under the home we have the monkey see, monkey do. Go in there, and that's the default place where the initialization system actually brings us to. So for instance, if I want to, I don't know, to say remove the entire bin folder, this is not going to allow me to do so, because I don't have proper permissions for that purpose. Same would be if I try, say, to create a directory, say, under the user folder, and I just call it test, for instance. So it tells me that I'm not allowed to do this, but using sudo, obviously I can. So mkdir, for instance, user and test. And if I just list the user, then we have the test. So we no longer need this, and I can actually delete this back. So rm minus rf forcibly and recursively remove the user test. Okay, let me show you the init script. So this is the entry point of where we enter the entire sort of a boot process. So we start with suppressing kernel messages, running command d message -n and the value of 1. Then we just clear the screen and print the logo to screen. So just to give an idea, the logo is, if I just cat the ads logo, this is the logo. Then let's just drop back to our init script. So then we mount system file systems. So these are absolutely essential for kernel to work properly. So we have the deft-mfs, which gives us the list of all the devices we have, the proc, the sys. Then we see the permissions. Just probably want to show you the contents of those folders for now. So if I say ls dev, I have a whole lot of devices here, and again, like this, all these are just emulated ones on the real hardware. I would also have my NVMe SSD drive, for instance, which I don't have here, etc. So if I say ls proc, then we have a lot of processes here. ls sys, we have the system related stuff. So for instance, we can see the network devices on the sys. If I say ls sys class net, what? Oh, sys. Yeah, we have the available networking interfaces. Yeah, and if config obviously works exactly the same way. So if I'm looking for the eth0, yeah, we have one. So the IP address has been received. And well, that's the standard IP address when you're running the system under the QEMU. Okay, let's drop back to the init script. And so once we are done with mounting system file system, the next thing to do is to provide the permissions. So we have two users, the root user and the monkey see, monkey do user, and also two groups, the root group and the group called stuff. And well, this is because the package manager I'm using, the one from the Tiny that comes from the TinyCore does need to have the group name stuff where the user belongs to. So that's the reason. I will also show you the files where the users and the groups are created. But for now, for those users we have, we have the file called sudos because this is essential configuration for the sudo command to work properly so that I could run other commands as the super user if I'm not allowed to do so as the monkey see, monkey do user, which is default user. Right. So essentially two things. So changing the owner for the root. So this is done for the sudo itself, and for the sudo configuration file, and setting up the specific mode for it so that it works as expected. And another thing is we do change the owner for this list of folders for the home, for the temp, and for the sysconfig. So, home is self-explanatory, but the temp and the sysconfig are used by the TinyCore package manager. So when we download packages, it needs to create some temporary files, and that's the reason why this access should be given. And since the TinyCore package manager is using the default user, it doesn't do sudo for this particular stuff. It does sudo for other things when like copying files back and forth, but that's a little bit another story. And yeah, also we say that everyone can do everything, and execute bit is being set for recursively for all the files and folders, like for all the files essentially under the home temp at sysconfig. So these lists are similar, right? Also, we need to create the mount tab, mtab file, which keeps track of the mounted things on the system. This is also used by the package manager. I could not do this if I didn't use that package manager. And this code you might be familiar with from the previous videos. So essentially, it loops over the network devices under the sys class net, which I've just been demonstrating. And then it just sets the device up, and then it calls the udhcpc in the background, and it runs the script as network shell to initialize the device properly to assign the IP address to it, essentially. And once it's done, it runs the asbin init. So let's first have a look at the network shell. So this script is essential for setting up the particular IP address. So say like this, IP address at, and then the IP and mask and interface. Those are the environmental variables being set up by udhcpc when it works. So that's the automated way to get the dynamically assigned IP address from the router. Okay, and when the IP is available, we print the IP itself, the mask, and the router that we received the IP address from. So hopefully that makes sense as well. And finally, asbin init. So there are many initialization systems for Linux. Systemd is probably the most well-known one, and although being criticized a lot these days. sys5 init is a bit more rare one. BusyBox has its own init, which lives under the asbin folder, and it's called init. Just init. That's it. Rob Landley, the author of Toybox, has written his very own stuff, and that's called whoamit, right? So, but the idea behind this sort of programs is sort of a similar. So it manages the initialization of the entire system when it just boots, and also it is responsible for handling events like rebooting, powering off. Well, that's the most simplest cases, obviously, like things like systemd runs a whole lot of daemons for various, this might be whatever, like dbus, for instance, or like ntp daemon for updating time and date. Many others, like I'm not quite sure whether X server for like the GUI stuff is also, that's probably, yeah, also treated to be as a service, obviously. So yeah, but with the BusyBox init, we have a very, very simplified way to control our system, and we have the only file to configure the has-been init from BusyBox. So if I just have a look at ads and init tab, that's the configuration file. That's all we have. So when the system inits, we just clear the screen. On restart, we call has been init, so literally calling itself. The idea behind this is that if you try to kill PID1, kernel would panic and your system would not be capable of like closing naturally, so that would be an error. It's not going anywhere. So on restart, we again like use this has been init. While on shutdown, we sync everything, and then it automatically does the rest. On Control Alt Delete, we do call the has been reboot, and when we try to escape from the shell, what it does, it just logs in back. So this line is quite interesting. So we have, well, the ctty hack is simply needed to figure out which tty device, obviously the virtual tty device, are we currently at, and it runs the console on that particular device. And login brings us to, well, it just enters the system as the monkey see monkey do user, and then it goes to the home slash monkey see monkey do, which is the home directory for that particular user. But that's not really that simple, because we also need to check like what happens in particular for the particular login. So now it's time to have a look at groups and users. So let's kickstart with groups. Those are just a little bit simpler. So cat ads and groups. Yeah, group like this. So we have the root group. The LP and no group are coming from the TinyCo Linux, and probably they are not even needed, to be very honest. Staff group with a value of 50 is essential, because that's the value that is hard coded under the within the TinyCo Linux. So just for compatibility reasons, I have this particular value. This X between the colons means that no password is needed, so both for groups and for users. And again, like the user can be associated with a certain group. So root user is associated with the root group, and monkey see monkey do user is associated with the staff group. And for instance, if I run like ls minus ld under the home folder, you see like it belongs to monkey see monkey do user, which is who is the part of the staff group, and this is owned by staff. But yeah, where did we specify this again? So we have specified this in the very initialization file here. So like to make sure that the monkey see monkey do or user that belongs to the group staff owns the home folder. The users we have, yeah, just to list the users one more time, just clear the screen probably, and say ads and password. So the root with the standard values of 00x again means that no password is needed to access as the root. So I don't care about security. The only reason I have this distinguishing between the root user and the monkey see, monkey do user is because of the Linux package manager, which cannot be run as root. Yeah, we got the tce-load under the bin folder, and this is actually the package manager, so that's a big file. So if we have a look at bin tce-load, yeah, like 295 lines of code here, does a whole lot of things. The basic usage is described in this tunnel help. What I really love about this package manager is that it's implemented as the pure shell script, and it doesn't even need bash to run. It just uses the BusyBox hash, or the default BusyBox shell, essentially. And it depends on the file called tc functions, which is available under the ads init folder and tc functions. So that's probably the very last thing to show before running the package manager. So if we go to say just cat ads and init and tc functions, no, not cat, but open within the text editor. Yeah, it's much bigger, but it's not only used by the tce-load, it's used by all the scripts on Linux. Okay, now let's fetch some packages from the Linux repository. I can probably show you using the wget first the repository itself. So if we navigate to https and then tinycorelinux.net slash versions 14.x architecture x8664 and tcz folder, and let's go. Okay, connection refused. Yeah, because it's not HTTPS, it's actually HTTP. Yeah, it doesn't use the secure connection. I don't give a fuck to secure connections, to be very honest. Okay, so here is the list of the packages that we have. So for instance, there is the built-in tool called something like tce search, if I'm not mistaken, but we can search the desired package using just the bare wget utility, so say grep, and I'm looking to install the CURL, for instance, and let's see if it is available. Yeah, we have the CURL step, so let's install the CURL. So tce-load and -w to download and I to install, but we'll keep things separate for now. So just downloading first because I want to show you how things have been organized. So downloading the CURL like this. And first it checks for the dependencies. So CURL depends on the CA certificates, OpenSSL, and yeah, probably that is it. Maybe something else. Now if we list the temp, no, not the app user. What is on the, no, it's not on the temp. No, that's sysconfig tce directory. Yes, optional. Yes, optional. And here where the downloaded files are actually living. So this tcz files are just the squashfs images. So what the installer does, it mounts the squashfs image and then it copies all the files to the init ramfs so that we could make use of it to run the package. So to install it, I can say tce-load and -i and CURL. Yeah, just to show you that I don't yet have CURL on the system, you see. Yeah, so now tce-load -i and the CURL. It says it cannot find the libSSL, but yeah, eventually it does manage to find it. And that is symlinked to the mounted squashfs file system, and eventually, yeah, I'm not sure why this message is happening there, but CURL is actually working after, as well as the OpenSSL. So if we just do OpenSSL shell is here, all good. And if we try CURL and say https example.com, it works like a charm and prints the output to the standard output. Okay, let's install something else. So, for instance, we can install text editors, one of my favorite topics. So let's do now tce-load and minus wi. Now I just combine these two commands so that the package manager would download and install the desired package. Well, the reason why this matter of like downloading and installation is been split, that's because um, Tinical Linux never leaves the init ramifast territory, as well as like my Linux distribution, Monkey also does the same thing. It never leaves the init ramifast territory, and if you have many packages being activated, like installed, essentially, that makes the RAM usage growing. So you may want to disable some just to save RAM if you don't have enough RAM, for instance. Well, obviously, probably you do have enough RAM, but anyway, so that's the reason behind. That's probably the historical reason behind this particular implementation. So they have split the downloading and installation of packages. Yeah, but probably all the package managers also do have this feature. But by default, you download and install. You can do just the download, but that needs some specific command line arguments, I believe. But anyway, so let's download and install Nano text editor. So you might have heard of the Nano text editor. So just first resolves the dependencies, file tcz and n curses. Okay, it doesn't find the file tc user under the sysconfig, but since there is no such a thing as a tc user, we just don't care. And this is only Nano specific, so we just may not care about this much. But if I just try to run Nano actually works here, and yeah, just can do things, and then escape. Same with Vim. Just no, I don't want to save the buffer. Clear. We can also install Vim exactly the same way. So let's say tce-load minus wi and Vim. And yeah, so it has a bit more dependencies. Yeah, but eventually Vim also works like a champ. So now the a bit of a downside is that quit. Yeah, just is that whatever packages you have downloaded and installed, next time you reboot, they would be vanished because this is the live CD. It doesn't know anything about what has been happening previously because everything gets written to the init ramifast. It only lives on the random access memory. It's not ever going to the hard drive. And Tinyco Linux has some options to deal with this. So it has the home folder being separately maintained and being is doing some backups. And also it allows to remaster the ISO image to to include those packages that you have installed. Many different options. I didn't yet provide any of those. Because my ultimate goal is just once I get done with installing things that I actually need, I will then just make an ISO once and forever, and I would be having all those packages I need. Well, the major goal that I had was to actually have Git. So just probably one last thing to show, because Git has plenty of dependencies. So just install Git here. It does rely on the CURL, and before I managed to set up the CA certificates properly to make sure that everything works, it wasn't really the option that much. The Git didn't work, but once everything is there, Git also works. Yeah, it doesn't even download the CURL because it's already there. So, like, yeah, if the dependency is already installed, it's not being downloaded. That's another nature of the package manager. So let's say git clone https and github.com, my username and my VICI text editor that I'm developing and showing you in my videos a lot. Essentially the only editor I'm using these days, the one I've written on my own. Okay, so downloads things. yeah, because I don't use git ignore to not upload the binaries to the repository. It's growing, so I need to clean up things one day. Okay, go into VICI, go into source, and here we have the source code for the text editor, and we have the executable. Yeah, by the way, this is the cross-platform one, so if you're in Windows, you use this exe file to run this under the Windows command line. Okay, so I think this is it in regards to demonstration of how the end result actually works. Now let's just power off from here. It won't allow me to do without sudo. So let's power off from here. Yeah, admin init does things for us, and it just ends the session, and the QEMU has been finished, and we're just going back to Linux Mint where I'm recording this video. Okay, so let's clear things. Let's list the sources of the monkey see, monkey do Linux. So again, I had many scripts earlier. Now I have just essentially one build script. So build script builds the entire system. We'll now have a look at that. ISO shell burns the ISO monkey see, monkey do Linux ISO to the USB flash drive. So let's have a look at the ISO first. So it's nothing special so far. So just reads from the user like where to dev-sdb1 or dev-sdb, wherever the block device address is, and then it burns things there. So it's quite pretty simple. Then if we have a look at the run shell, it just the command similar to what I've been using now to run the ISO under the QEMU. And the most interesting one is the build shell. Apart from that, we have two folders. The one is monkey see, monkey do. This is the working folder where things are being built during the process. So say the Linux kernel gets downloaded here and gets built here. The glibc, BusyBox, and all this stuff, and also ISO folder being formed here as well, so that to create the ISO from that folder. So for instance, if I have a look at the ISO, so it has the boot, then it has the BZ image, which is the installed Linux kernel image, and the root cpu.gz, which is the root file system compressed one. Under the grep, we have the grep configurations. So just I've been showing you this a lot of times, but just one more time to show. So the menu entry monkey see, monkey do, which you've seen on the screen. So the kernel lives at boot / bz image init rd. In our case, this is essentially init ramfs, but in the configuration, this is still called init rd. Boot / root cpu.gz. So this is the boot configuration. And another interesting folder is the root. So this root is heavily used to create the eventual root file system. Like for instance, here under the lib, we have this cheating. So the shared objects that I've grabbed from the tiny-linux lib folder, because yeah, I'm not quite sure why exactly these libraries and not others. Just because I'm relying on the tiny-linux package manager, I need this to have, because the tiny-linux packages are not going to work without these libraries, because they are not set as the dependencies for those packages, which is so weird because they should be. And yeah, this really violates the idea of having the core and the extend and the packages to extend the system, like the tiny-linux claims to be. Yeah, I don't know, maybe some historical reasons for that, I have no idea, but that's how things work. Under the firmware, we have the Wi-Fi driver that has been demonstrated when the system has been running, so that's the same thing. But it doesn't have the glibc. Glibc gets compiled, and then the files are being copied in here. Well, not in here in particular. So this folder is merged with in other folders and files, and eventually the root file system gets like the eventual root file system that later gets backed into the root cpu.gz is available under the monkey see monkey do and rootfs. So this is the one that we're actually booting into. It has the symlinked lib64 is just a symlink for the lib folder, because that's required by the BusyBox to see where the libc libraries are available at. Otherwise it's simply not going to boot. Okay, so yeah, probably let's go and have a look at the main build script. So again, I've been rewriting this a lot of times. And again, monkey see monkey do folder that I've just demonstrated, it's now available when you just download, if you just git clone the repository. It appears when you actually build things from sources. That's another important thing to bear in mind. So if something goes wrong, we just escape from the script. Then I specify the versions for the kernel, for the glibc, for the BusyBox. This is the current working directory. So in the previous scripts, I was doing relative cd dot slash dot slash dot and so on. That was really annoying and not really easy to maintain. So finally, I'm using the normal definitions for directories. So the parent working directory, the kernel directory, glibc directory, BusyBox, sysroot. So sysroot is not exactly the same as the rootfs. So sysroot is it contains the mostly the libraries and the headers as well to make BusyBox compiled. So that's the intermediate folder to have, just to have the BusyBox compiled. It's not. It then sourced to create the root file system, but initially I just copied everything from the sysroot to the future rootfs, but that resulted in the ISO with the just Linux kernel, BusyBox, and glibc of 75 megabytes. That was too much. So by stripping down a lot of things, I managed to have only 23 megabytes, which is really cool. Also, I've stripped the debugging flags or information from the binaries and from the libraries. I could have done this during compile, but it didn't, because I could do this later, and that has reduced the size dramatically. Anyway, so then we just have a few functions. So the first function is to get the dependencies. So just to have the tool chain capable of building the Linux kernel, glibc, and BusyBox. Build init just destroys, deletes the monkey see monkey do directory that we've just seen and creates the new one. Okay, if it's not there, nothing happens, it just creates the new one. So once the monkey see monkey do working directory has been created, then the rest functions make use of it by going in there first, and then for Linux kernel, for instance, it first just downloads the kernel, then extracts files, then goes to the kernel directory, makes the default configuration, then grabs the configuration that already exists, and now it has been stored in a different place earlier. Now it's stored under the root, which would be later the part of the actual rootfs, but now it's under the var local config kernel.cfg. Then just a compiling kernel. This produces the BESA image under the Linux directory arc x86-64 boot, and then we have the BESA image. I hope that I spelled the path properly. Then glibc, something wrong with the indentation. Okay, so again, go into the working directory, downloading glibc, extracting files, go into glibc, creating the directory where we're supposed to be building glibc, the one we're supposed to be to install the glibc, go into the build, configuring and specifying the prefix equal to root, nothing means root, then compiling glibc and installing to the destination directory, which is this uppercase glibc. I have a separate tutorial on how to do all these steps in details while typing commands and talk through. That's the previous video within this playlist. Build sys-root is where things are starting getting interesting. So we're creating the sysroot and the user folder under the sysroot as well. We copy everything from the installed glibc to the sysroot. Also, there is another additional folder that is being created after glibc installation, which also the uppercase glibc, but in the different slightly bit different place, and it has the include folder in it with the headers required for the installation of BusyBox. Then we copy the actual libc .so files to sysrootlib that would also been required by the BusyBox installation. Otherwise, it's not going to work. Then, here I'm cheating a little bit, so still not all the required headers at this point are available for compiling BusyBox. So I just cheat and use my Linux Mint user include headers that I have there, and I copy them to the sysroot. Not copying, just syncing, like merging those headers to the sysroot. Then I do the symlink for the include and I'm creating the user include, which is the symlink, which points to just the include, the root / include, and the same for lib. So user lib points to just root / lib. Well, it's not root here because it's relative, but it's actually the sys root, meaning the sys root in this case. All right, then build BusyBox. So after we have prepared the environment to compile BusyBox under, we go to the BusyBox. We go to the monkey directory again, download a BusyBox, extracting files, go into the BusyBox directory, creating default configuration. These two lines are very essential. So first we set the sysroot folder configuration to the sysroot folder that we just created. That's very essential. And also extra C flags, this -l sysrootlib gives us an idea of where to look for the .so files that are used during the compilation. Then we just compile BusyBox, and finally we install BusyBox to the BusyBox folder that gets created automatically, thankfully. And finally, build rootfs. So this function results in the folder called rootfs that contains exactly all the files and all the folders, all the libraries, everything that would later be available under the target system. So again, rootfs and sysroot are not the same thing. So sysroot is used to for the compilation purposes, just to compile BusyBox, and rootfs is the like folder essentially where all the files for the Linux distribution we're building are living in. So just cleaning up the previous rootfs, creating a new one. So the first line, so you remember we had the root with cheating, like I said, like having the libraries from the tiny core Linux, having the RTW88 Wi-Fi firmware specific to my particular hardware, and many other things. Like it has the sudo, by the way, it has the sudo and the configuration for sudo there under the bin folder as well. So we're not compiling sudo from scratch. We're reusing one from Tiny Core Linux again. Yes, I was cheating. I've been cheating a lot during this project, but yeah. Since that wasn't really essential in regards to understanding how things are actually working, I thought that's just a good enough trade-off. Okay, then we copy the libc libraries that are required to run the BusyBox, because without this, BusyBox would simply not start. So this libm so6, libc so6, libresolve is needed to for the DNS resolution when we run the wget utility to download something from internet. So and the configuration for this one lives in the ads result.conf with the name server 8.8.8.8, which is the Google DNS server. Then this is another library needed for BusyBox to run. Then what? I do copy the LDD, which is shell script, by the way, from the sysroot, and before that, it came from the glibc installation. So when the glibc gets installed, LZD is the par. It's living under the bin folder. So we just copy the LZD to our root of host slash bin slash LZD so that we can check for the dynamic dependencies of the given binary executable. Then I'm changing the bash to shell under the LZD because for some unknown reason, because probably I messed up something with configuration. It just creates bash in the shebang line, but we need shell because we don't have bash on this system. So I'm just manually changing bash to shell for the LZD. Since this is a shell script, it's easy to do. Finally, we symlinking the leap, the root slash leap. So we're creating the lib64, which is the symlink of the lib. Because again, that is required by the BusyBox lookup that is looking for the shared object libraries to actually boot. Finally, we remove Linux RC from the root file system, which came automatically when we copied everything from the BusyBox. And since we're not using init RZ but init ramfs, we don't really need Linux RC, so we just get rid of that. Then these lines are quite interesting. I've taken them from the Minimal Linux Live project by Ivan Davidov, who introduces this cool trick. So we can strip the G minus G. I think this stands for debugging. I'm not quite sure how to properly say debugging what, but like you can compile the program so that you can run this through the debugger step by step, and some additional like symbols are being added to the eventual binary executable to make it possible. But we can later strip those symbols, and this results in reducing the size dramatically. Like essentially, like initially I had 75 megabytes, then I now have 23 megabytes. But not only because of this procedure in particular, because I also didn't include unnecessary stuff. But anyway, this is really helpful to if you want to make the size of the target ISO smaller. And yeah, finally, just the function to build the ISO image. Well, nothing really special here. So we just updating the ISO directory, go into monkey root file system, then pack in root file system and resurrect with the when we did everything. So first we create in the find all, recursively goes through all the files, CPIO creates the CPIO archive, then this gets piped to the gzip and to have the tar.gz file as a result, and then we copy this outputs to the standard output. We redirect this to the file ISO directory boot root cpio gz. Then we copy the kernel there under the boot, and then we copy the grep configuration as well, because otherwise it's not going to boot. Finally, we use grep mk rescue to create the ISO, and we can already boot from that ISO. Now, what I'm doing when I'm debugging this, I'm just commenting out all these steps, because all these steps are needed to populate the monkey working directory with what we need. And once that is done, we no longer need this, because otherwise we don't really want to recompile the kernel and build everything from scratch every time we want to add a single file to the root file system image, right? So we just can comment this out, and then I'm using just build rootfs and build ISO, so that if I make some changes to the configuration file, so maybe just add something to the root file system, that's how that's how I can update things without unnecessary pain. So yeah, guys, I think this is it from my side in regards to this project. And yeah, so now finally, I have the Linux distribution that I've compiled and configured completely on my own, that is capable of using Tinycore Linux Package Manager, which I really like a lot. And you might be wondering why I'm not using Tinycore Linux if I love it so much. Well, there are a few reasons. Well, first is because by default it uses the syslinux bootloader, and with my UEFI boot, it's no longer relevant, it's just not working. So I could have used grep for Tinycore Linux, but many of Tinycore Linux boot codes are related to syslinux. Probably there is a way to port this to grep somehow, I don't know, maybe, But yeah, I just didn't really put enough time and effort in that research. So I just decided to make my very own distribution instead, where I can control everything. So like for those fans of distributions like Arch Linux, for instance, where people really enjoy building everything from scratch. I need to say that, say, when you have the Arch Linux or the Tiny Core Linux or whatever Linux distribution that when you install it, you come up with just a terminal and the blinking cursor, and then you can just install everything using the package manager and then configure everything. But that is just the starting point in those operating systems. But I wanted to go even deeper because providing the environment that do allow you to install and configure everything using the package manager is really tough work. That's the tough job. So you really need to put lots of time and effort to provide such a system. So that was my goal because I was really interested in exactly building the system that would be like conceptually similar to like either Tiny Core Linux or Arch Linux. Well, obviously, Arch Linux is much better because it's using systemd for initialization. It's more flexible. It may do much like more things. Also, yeah, it's not living in the init ramifs. I don't know, but I don't believe it does. Tiny Core Linux do, but Arch Linux probably don't. Probably doesn't. So yeah, but anyway, building things absolutely from scratch is incredibly insightful thing to do, and this is really. I need to say that I've learned so many things about Linux just by doing this, and I would never learn this if I used somewhat an existing Linux distribution. Because again, like, I was using Tiny Core Linux a lot in the past, but under the Tiny Core Linux, you just use the package manager and you just install all the packages you need, and everything just works automatically, and you just end up with a Linux distribution that really looks like Linux Mint eventually. So you don't really face any troubles of like doing things on your own. So you then just remaster the ISO and have the snapshot of the system that has everything you have. Well, from the practical perspective, obviously that's the good thing. And again, from the practical perspective, like you can just download Linux Mint and it already has everything you could have ever imagined. If it doesn't, you can use the wget package manager to install something and be happy with that. But yeah, this exercise to build Linux from scratch is really good when you want to learn how Linux works internally. So this is really insightful journey. This has been really insightful journey, and I wish anyone interested in learning how Linux actually operates to walk through the steps I've been through, because yeah, you end up with a very valuable experience that would give you uh, the understanding of the flow of Linux, of how it works. This is it from my side, guys. Thanks for watching. Hope you enjoyed the video. Hopefully this was useful to you. See you next one. Take care and cheers.